My name is Christian Gerlach, and I'm a professor in psychology at the University of Southern Denmark. Today we are going to discuss a hot topic, namely gender differences, and it's a topic that a lot of people have different opinion about. So I think it's going to be fun. I think the scientific approach to the gender debate is important because there are a lot of stereotypes out there that turns out to be actually not well founded. And it seems to affect the way that we organize schooling and also the educational system. So I think it's important to get a nuanced view of what is right and what is not so right. What I'm going to tell you today, I hope that it can make you think about the stereotypes that you have about your own sex and the other sex, and not to get caught in kind of beliefs about what people can accomplish and what they cannot accomplish.
Thank you for the applause, and thank you for having me here tonight to celebrate International Women's Day with you. But I also come here to set things straight. Hence the title. So, I'm going to tell you that the difference between women and men and women is that women do women things, whereas male do male things. That's the difference. There's no more fuss. Except, of course, for the slight difference in some women do male stuff and some males do women stuff. But except from that, it's pretty clear. So, I could thank you now for your attention. Probably a bit too cheap. But the truth is, I'm a bit nervous about the topic today. It seems that most people have an opinion about it. Some people even have strong opinions about it. And I don't want to offend anybody, so I just thought perhaps not to say too much. And then we could just have a beer, right? But then again, that won't do. But it's complicated, right? It's complicated because when somebody says gender or sex, some people think, that's a biological term. Other people think, no, that's not true. It's a cultural construct. And some people even think both, some sort of mixture. And of course, that complicates things. But there are a lot of opinions out there, and just a bit of net surfing will show you there are a lot of stereotypes as well. So I just grabbed a couple of stereotypes to show you. The female brain, here you have it. Yeah, right. We also have a male brain, looks like this. But the question tonight really is, these are stereotypes, but is there a grain of truth in them? I'm going to try to answer that question here tonight, especially for you. So the outline of my talk is, it's divided into 4 sections. First, I'm going to talk a bit about brain development. Then I will have a few notes on hormones and also on statistics. That sucks. But yeah, it can be tedious, but science sometimes is tedious, right? And I think it's important to have those grounds covered in order to put the juicy parts into perspective. The juicy parts being cognitive differences and brain differences. And we will return to them after a break, where we can get some beer, right? Yeah. But let's start with some facts. The smallest functional unit in the brain is the nerve cell. And it looks something like this. So it comprises a cell body and sort of all kind of tentacles moving out from this body, known as dendrites, if you're familiar with that term from biology. And on these tentacles are located a bunch of receptors. And these receptors can act to the degree that there are signal molecules that get attached to them. If they pick up these molecules, they can open small pumps in their membrane, and they can actually change the electrical circuits in the cell. So it can generate a current that can travel down the output unit here, which is known as the axon. And down here, we have some axon terminals. So if there's a current generated, it will travel down here. And some new neurotransmitters, the signal substances, will be released, and they can pass a small cleft and get attached to another neuron's dendrites that have receptors for these kind of neurotransmitters. So that's the way the brain cells communicate. And we have a lot of those. By the time we are born, we will have something in between 15 to 32 billion nerve cells. And it differs across individuals. Now, these are just estimates because it's pretty difficult to count them, right? There are quite a lot. But we are born with more or less all the brain cells we're ever going to have. We might generate some new ones, but not compared to how many ones we are going to lose. So by the time you reach the age of 70, you will have lost approximately 100 grams of your brain, or 80%, due to the neurons dying. Oh dear. Another interesting thing is that how fast can neurons communicate? The fastest neurons are able to send 200 messages per second. And that might sound like quite a lot, but compared with, for example, the computer you have at home, a processor in a computer can conduct about 3 billion signals in a second. So how come it be that we are so smart to everything besides calculating things compared to computers? It's because we don't have, for example, in your computer you might have 4 processors. We got 15 to 32 billion of them. And also each processor or each nerve cell can be connected to up to 15,000 other nerve cells. So there's a lot of communication and a lot of cross communication. And well, this is just a picture taken with an electron microscope showing a neuron, and you can see the axon terminals, the synapses where other cells connect to this neuron that you have here with its cell body and its dendrites. Now, for a long time, it was assumed that the human brain was fully developed by the age of about 6 to 7. And why is that? It's because at this point in life, the child brain weighs approximately the same as an adult brain. So people thought, well, it's all over by the year of 6 or 7. And that's why children look so peculiar, right? They got adult heads and tiny bodies. So the development is just to stretch them out a bit, right? Of course, it turns out that it's not that neat. It's more complicated than that. And some evidence for this comes from trying to measure how much sugar does the brain eat at certain points in life. So here you can see energy consumption as a function of age. So you have energy consumption, you can just think of it as amount of sugar going up here, and you got age going over here. So when we are born, the newborn baby consumes about half as much sugar as the adult brain. But immediately after birth, there seems to be a huge increase in the amount of sugar that their brain needs. And at some point, around 7 to 8 years, it levels off. And it gradually reduces through adolescence to reach adulthood, where it reaches a plateau and stays permanent. So, but about this time, the child brain uses 4-fold as much sugar as the adult brain uses. That must signify something, and it does. I said that we are born with all the nerve cells that we ever going to have, more or less, but that doesn't mean that they are fully matured by birth. They are not. All these tentacles, communication pathways are not necessarily established by birth. They are grown out after birth. So following birth, all these neurons will sprout new tentacles, making contact with new nerve cells that they can communicate with. This has a fancy name known as synaptogenesis, the formation of new points of contact or new synapses between the cells. Then there is another process. It's sort of the reverse process. Some of them are eliminated or cut out. This is known as pruning. So you can see this is the springtime in the brain, and here comes autumn. And it seems to work the way that the synaptic synapses that are not used are actually lost. So put it in a slogan, use it or lose it. If you don't use it, it will be lost. So apparently these cells are fighting in a Darwinistic way, survival of the fittest. So the cells that are doing something with a purpose are kept, the others are eliminated. And that's a pretty neat arrangement, because it means that we don't need to hardwire everything from the beginning of life. It's not everything about the brain that is determined by your genetic makeup. Because what is it that determines which cells are used or not? It's actually the environment. If I use all my day for playing tennis, then all the tennis areas of my brain, they will be fully developed and make dense connection with one another, whereas the rest of the cells, they will get pruned away. That's pretty neat. But that means that it's actually the environment that is also shaping how the brain is organized. And this happens primarily in childhood. This happens mostly in adolescence. It also happens with exotic species like me, who have reached a certain age, but not very much, I'm afraid to say. I'm pretty much stuck with what I have. It's too late to make much of a difference. So what happens when you are past adulthood, adolescence, is that you can still do some tricks. You can still weaken or strengthen some of the connections that you already have. But it's very few new connections that are made, and not so much pruning either. And it's probably these effects that we are seeing in the sugar level of the brain. So we are born with all the cells we are going to need, but here they start making all these connections to one another. And here we reach a peak, and then it goes down. Here comes the pruning phase, and here you reach my level, where things are sort of put in stone, not so much modulation left. So that's one thing that's going on. There's also another thing going on. I told you that the neurons work by passing currents, and they work just like the cords you have in your home. They are much better at transmitting this current if they are insulated, just like the cords you have to your own equipment, to your mobile phone or what have we. Now, many of the cells when we are born are actually not insulated, but they will be. They will develop these kind of small sheets, known as myelin sheets, that contain a fatty substance, which is myelin. And that works to insulate the axon. And it's actually support cells that wrap themselves around the axon. And that means that the electrical current does not need to crawl down slowly here, but it can actually jump in between these spots. And that makes their transmission much more efficient than it is otherwise. And a lot of these cells are not myelinated from birth, but they will be following birth. So that's another development going on. And as you can see here, the gray, the body and the dendrites are gray, and they would actually be if you look to it in a microscope. And also this fatty substance will be white, precisely because it contains a lot of fat. So you can actually distinguish between two different kinds of substance in the brain. We have gray matter on one hand, and we have white matter on the other. And the gray matter lies on the surface of the brain, whereas the white matter, the communication pathways, lies in towards the middle of the brain. So I'm just going to run you through slides through the brain here, and you can see the difference between the gray and white substance. Wow. Okay, but we can actually use this for something. And that is that the ratio between gray and white matter will differ as a function of development, because there will be much gray matter at the beginning of development and not so much white matter, and that will slowly reverse as the brain matures. So if we can measure the degree of white and gray matter, we can use that as an index of brain development. And this is what is portrayed here in this figure. So the warm colors signifies areas of the brain where there's more gray substance compared to white substance. And the cooler it gets, the more white substance will come compared to gray substance. But even in the more or less adult brain, there are brain areas that are not fully matured at this point. And what exactly does this mean in terms of functionality? Well, the increase of gray matter, all these synapses, means that you have a large learning potential. There's practically no limit to what you can learn as a child. Of course, genetics makes a window, but it's the environment that determines where in this window you're going to end up. The downside is that you're not very effective as a child. If you make a grown-up and a child do a certain task, put them in the scanner and see what's going on, you will see that the child is using more different brain areas and larger parts of the brain to solve the task at the same level as the adult. So a lot of learning potential are not very effective. So this is the comfort for me here. I'm moved over here. I have a lot of white matter. So I'm quite effective at what I have learned. Unfortunately, I'm not very good at learning new things. That's the downside. But all these things, just to put it into perspective. So this means that brain development is actually determined by two major factors. On one hand, we got genetics, the synaptogenesis in the brain, and on the other hand, we got experience, or you can say the difference between nature and nurture, because it is also experience that carves the way the brain looks like. So the brain will determine partly how you handle your environment, but your environment will work back to shape your brain. And we also know from epigenetics that the environment you are in can actually turn on and turn off different parts of your genome. So it's quite complicated. That also means that our brains are different. Our brains are just as different as our faces are. So here you see two different brains. Well, by and large, they look similar, but when you look at the details, they're actually not quite alike. And that is true even for monozygotic twins who've got completely the same genetic makeup. Their brains also structurally are different. And that's because the environment has shaped them in different ways. Why have I talked so much about this? I've done so because we often jump to the conclusion that because we can see a difference in female brains and male brains, we think, aha, it must be biology working. It must be a genetic determined difference. But it need not be. It might as well be an environmental difference. If you consistently treat men and women differently, then you ought to see it reflected also in the brain's organization. Okay, here comes the next tedious part. Hormones and statistics. I will not have a lot to say about hormones, except for the fact that there are so-called male hormones, androgens, and female hormones known as estrogens. Now, the interesting part is that both males and females have male and female hormones. What difference between the sexes is the level of these hormones. Another reason, or the main reason I have much to say about sex differences is that it's very difficult to relate differences in hormones to cognition, and especially to differences between the sexes. I will have a little to say about hormones later on. Suspension. But not much. So this is the last slide about hormones. So what you can see is that the hormone levels differs during pregnancy, where the amount of androgens are much higher in the male than in the female. Now, after birth, they're actually on level with one another until adolescence, where it sort of go in two directions, right? So by this time, women will have larger amounts of estrogens compared to men, and men will have more androgens compared to women. But they will still have both kind of hormones. Another thing is that the effect that hormones have on our behavior tends to wear off the older we get. So the impact of hormones becomes less and less important the older we get. Then another note, and an essential note, about classification. What does it even mean to be a member of a class? The women class or the men class? In biology, class has a very specific meaning. And in biology, it's known as a taxon. And a taxon is defined the following way, that members of a given class have a greater probability of possessing certain properties characteristic of that class than do non-members. And I've listed some here. These are characteristics of the feminine gender, a vagina, not so much facial hair, and comparably larger breasts than we find over here. And here we find, well, a penis and heavy facial hair. Well, that's not the interesting part. That cannot come as a great surprise, right? What is more interesting is that the properties within a class often have limited variation, and the most important thing is that there is rarely any correlation or relationship between how they vary within the class. Now that's interesting, because it means if you meet a guy with a dense beard, I hate to be the one to break it to you, but that doesn't necessarily mean that he's very well equipped, because there is no such correlation. And that actually defines what a taxon is. So let me give you another example. Some people think that broad shoulders is very masculine, right? And small shoulders is more feminine. Other people would say that large breasts is very feminine and small breasts are more on the masculine side. Of course, there are exceptions, right? But if these two characteristics work as a taxon, then we would expect males and females to occupy different spaces in this graph, like this. So there will be very little overlap between them. They will be far apart. But within the class, for example, we will have males with broad shoulders and somewhat larger breasts, compared with other men who have broad shoulders, but actually not so large breasts. There's no correlation within the class, and not here either. So that's what defines a class difference in terms of biology, at least. But let me give you another example closer to what I'm going to talk about later on, when you suffered a bit more of this. Aggression. Some people think that high levels of aggression is something very masculine, right? And low levels of aggression is more on the feminine end of the spectrum. And we could say the same about empathy. If you are very empathetic, then it's more feminine. And if you don't have high levels of empathy, that's more masculine. Some call it toxin masculinity. But that's another story. If these two characteristics also behaved as a taxon, we would expect them to be, again, separated in this space. And it would be a class difference. However, it might just be the case that they actually do not spread out this way. Another possibility is something like this, where we see the males occupying more or less the same territory and the majority of the women here the same, but also that there is an overlap in the two distributions. If this is the case, we no longer have a class difference, then we have a graded difference, which means that we can have actually feminine males occupying this part of the spectrum and masculine females occupying this part of the spectrum. So just to get and give you a small appetizer for what we're going to talk about later, here are a few examples of what counts as class differences and graded differences. So physical strength seems to work pretty much as a class difference. Men are generally stronger than women. Of course, there are exceptions, but by and large, this is the case. Whereas when we come to other things, more psychological and social things, it turns out that class differences are not the case anymore. We talk about graded differences. So sexual attitude and behavior, social intimacy, empathy, or for example, interest in science are graded differences between the sexes to the degree that there is any difference at all. And now comes the statistical part. If I was able to measure the intelligence in the whole Danish population, I would get a distribution looking like this. Most people would be in the middle, here. Actually, about 70% will have an IQ between 85 and 115. But then there are some very clever people, but there are not many of them occupying this territory. And then there are some not so smart people, but not many of those either occupying the territory down here. So it turns out that when we measure psychological constructs, that is cognition, that could be memory, face perception, language abilities, what have we, it turns out that we get this kind of distribution. The bell curve, it's also called, or the Gaussian distribution, if you're into mathematics. Imagine now we wanted to figure out whether there is a gender difference in intelligence. Haha. And let me tell you from the start, there is not much evidence to suggest that's the case. It's highly controversial. And I don't believe in it, but let's say, for the sake of argument, that we want to find out whether it's true or not. We can't measure the whole Danish population. So what we will do is that we want to collect a random sample of males and a random sample of females, and then we look at the distributions. We calculate the mean IQ score of each group and see if it differs. It could turn out that it looked like this. There is a difference in the mean score. In this case, males are a bit below the females. But you will also notice there's a lot of overlap between the two distributions. So even though women on average are more intelligent than men, a lot of the men will be more intelligent than the not so highly intelligent women, right? So that's one possibility. Of course, they could also completely overlap, which we think is the case. I've shown that here, because you can't see it. It's totally cancelled out. But of course, there's another possibility, and that is that the two distributions are even further apart. In this case, we would say, right, there's a huge difference between the two sexes in terms of intelligence. In the latter case, it would actually mean that if I knew this distribution and you gave me an IQ score of a particular individual, I could make a pretty good qualified guess about whether this score came from a man or a woman. So that means that in the latter case, gender would actually account for quite a lot of the variance in intelligence. In this case here, not so much. So, why go into details with this? It's because the devil often lies in the details, right? It's not seldom to find people claiming that now we have found a significant statistical difference between men and women. And it just might turn out that, well, that is true. If you have very huge samples, you can find differences that are statistically significant, not in everything, but in quite many things. But what you really want to know is how large is the effect? Don't settle with just a significant difference. You want to know how large is the effect? How much of the variance can be explained by gender or sex? Right. And luckily, we have a statistic that can do just that. It's known as Cohen's d. And this is actually also known as an effect size. And what it does is that it takes into consideration not only the absolute difference between two means or averages, but also calculates the absolute difference seen in relation to the amount of variation around each mean or average. And it works as a ratio. And for those of you who just love formulas, this is the formula, right? So what we have here is the mean from one sample, the mean from another sample, and the variance for the two samples. So because it's a ratio, the larger the absolute difference is, the larger the Cohen's d will be. But also, the larger the overlap in the data, the smaller Cohen's d will be. And it takes into consideration both things. And now, of course, for those of you who are not familiar with statistics, it won't say you that much. So here's a rule of thumb, because I'm going to use Cohen's d in a while. This is the reason that I have to drag you through this. So the rule of thumb is that if Cohen's d returns a value below 0.2, there is no or little effect. There might be a statistical significant effect, but it doesn't really account for much of the variance that we see. So you can just ignore it, even though it's significant. Probably doesn't mean a lot. If it returns a value between 0.2 and 0.5, it is termed a weak to a moderate effect. Now you have something that can actually tell you something about the variance and how to account for it. And if you have a Cohen's d that is larger than 0.8, you have a large effect. Again, these are rules of thumb, but try to keep them in mind. Okay, understand? We're going to return to them. Okay, and the reason why is that there are quite a few papers out there looking at differences in the psychological domain. Earlier this morning, I made a search in a large database containing publications within psychology. And I used the following keywords: human, sex/gender differences, and cognitive mental. And I only wanted to look at peer-reviewed papers that were published in English and were whole reports and not just abstracts. So that should pretty much narrow my search, right, to what's important. So what's the result? Quite a lot of papers, right? 88,702. It's probably larger now. So, in the next couple of hours, I will walk you through these papers. No, of course I won't. It's not doable. But luckily, other people have done so. And what they usually do is, if you want to look at something that is stable, something that is just not a fluke from one study, you want to see reproduced in other studies. And one way to go about it is actually to look at all papers within an area and to see if you can find effects that goes in the same direction. And what people usually do is that they calculate, guess what? Cohen's d for each study, right? Is there a difference? How large is the difference? And the good thing about Cohen's d is that you can just pool all these Cohen's d's together and just compute the average. So if you have an effect that goes again in the majority of the studies, you will also find it when you take the average. If it only appears in some studies but not others, or as is often the case in this area, some people find that men outperform women and others find that women outperform men in the same task, it will cancel each other out. So what you will be left with is stable effects. These types of studies are known as meta-studies, and I'm going to return to them after the break. So, thank you for hanging on, and we get to the juicy part in not so long. Thanks.
My name is Michael McGee, and here at Science and Beers, I'm the project manager. So I believe that science is for everybody. We all benefit from science, and therefore science should be made available to everybody. And so with Science and Beers, we want to make science available to everybody by these open access lectures, but we also want to make it fun. And how do you make it fun? With a couple of beers. We are in the student house, Odense. Science and Beers started here 2018. It started off with a small event, about 50 people, but over the seasons, I think Science and Beers has grown in popularity. So Science and Beers was founded here at the student house, but it exists today in Aarhus and Aalborg and soon Copenhagen. So we're talking about, by the end of this year, a nationwide science communication platform. So it's Friday night. It's Friday night, and we normally host Science and Beers on Friday or Saturday nights. Who comes to a lecture on a Friday or Saturday evening? Science and Beers people do, because Science and Beers, it is fun. We're going to have a party tonight. We're going to start off with a bit of a laugh, and then we'll have a few drinks, and we'll also learn something. So, and we will finish the night actually downstairs on the stage with some karaoke. So, as I said, Science Beers is open for everybody, and it's sold out tonight because we've existed for a few years now, and people know that they're going to have a good time at Science and Beers. We use our channels to encourage people to come to talks outside of their area of expertise. So if you're an engineer, come to a social science talk, and if you're a social scientist, come to a biologist talk. So there's a lot of students, and then there's a lot of people that have graduated as well. Because one thing you miss whenever you leave university is access to information. At university, you don't realize it at the time, but you have access to all of these lectures and smart people all around you, and you lose that the minute you graduate. So with these open access public lectures, you can come and be a nerd, and we want to really support the idea that being a nerd is cool.
Just need to turn myself on. Okay, right. So, let's get to the juicy part. Cognitive differences. As they say in Danish, er der noget at komme efter? Loosely translated, is there anything to come for? And apparently the answer is yes. At least according to the Sun. This is what the Sun says. The male brain, characterized by being good driving, funnier. I'm so happy with that. And a bit more impulsive, perhaps. And then the women are better reading and writing. They have good long-term memory, right? They are better at learning languages. And all these things are apparently connected to the brain. So in short, men are fast, funny, and furious, and women are, well, they're a bit boring, right? At least according to the Sun. But is there any grain of truth in this? Now let's take a scientific look. So what I'm going to present to you now are these kind of meta-analyses where we look for effects that are stable across a lot of studies. And these studies, these meta-studies, have in your back of your mind that they can cover thousands of individuals. So that's the kind of figures that you want to rely on. So the first thing here is language skills. Is it true that women are better at language than men? Well, look at Cohen's D. Da 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 da. You have it here, right? And here you just got different meta-studies covering different subfields within language. And for this slide and the next, if we have negative values, it means that women outperform men. And if it's positive values, it's the reverse. And it could just as well have been the reverse. I don't know why there is this tradition in the literature, but there is. Right, can figure out yourself. Okay, but what does it say? basically it seems that, well, it might be the case that usually women are a bit better off than men at language. But if you look at the sizes of the effects, they are so small that you would call them insignificant, doesn't matter, or just very small. So, in the case where we have the largest difference between the sexes is in reading in this particular examination of different countries within the OECD. And this is an effect size that is weak to moderate. And it's perhaps better to see how much of the variation can this difference account for in terms of how much people differ in total in reading. And even though we have a somewhat reliable difference here, with women being better than men, it can only account for 4% of the variance in how good people are to read. The rest, the 96%, has nothing to do with which sex you have. So it's a tiny difference, right? What about math? Is it true that men are better at math than women? Bob, bob, bob. Not really, right? We have some positive values, mainly positive values. We also have a couple of negative ones. But again, they are small. Pretty small. They're so small that they're negligible. The largest one of them is at 0.22. And that amounts to 1% of variance explained. So here we have math general understanding in adolescence in the USA. We find a sex difference, but it can only account for a tiny 1% of the difference in how good you are at math in general. The rest, the 99%, is caused by something else than which sex you have. So it's a tiny difference. Even though it might be statistically significant, doesn't really matter. So let's move to a new area, spatial abilities. And what is a spatial ability? It has something to do with your ability to perceive spaces, right? And to navigate in your surroundings. Now we are getting somewhere, right? All meta-studies suggest that men outperform women in this case. But again, the effect sizes are mostly weak to moderate. We have one effect size that just approaches being large, at least in one study, and that's mental rotation. But even in that case, we still have to keep in mind that the difference can only explain 40% of the variance in the ability to mentally rotate objects. The rest has something to do with other things than sex. But this is actually the most stable, the largest cognitive difference that we can find. Is it due to biology? Who knows? It might not. Some people have tried giving people these kind of rotation tasks. And if you tell men that if you're good at this, you will probably be good at designing clothing, performance deteriorates. Totally. They can't do it. Right. So you can actually affect it. But what is mental rotation anyway? It's your ability to perform a task like this. To see whether the figures on top, can you rotate them and overlay them so they are identical? Or are they mirror versions and the same for the one below? Males tend to be somewhat better at this than females. But again, we are talking about a greater difference, and it's not that huge. But it's the biggest one we have in psychology. Sorry, that was a kind of spoiler, right? For the rest of the talk. Okay, but let's look at some other domains, nevertheless. So, if we look at memory, remember the sun? Women have better long-term memory than men. Is it true? Well, they might, but it's a tiny, tiny difference again, right? It's in the same direction across studies, but it doesn't account for much of the variance. Less than 1% again. Doesn't really matter. What about executive functions? Now, what is executive functions? It's your ability to make a plan, make decisions according to your plan, stay on your objective, inhibit impulses to do something else. You know, the kind of grown-up stuff. Nothing. No difference whatsoever. What about comprehension of science? Again, nothing, really. Pretty boring talk, right? Nothing here, nothing there. So let's dive in. Let's zoom in on some differences in literacy and math and science understanding across countries. Will that make things different? Well, sort of. What you can see here is that it actually differs across countries. So we have a difference in reading ability. Girls tend to outperform boys, but it differs from country to country, and the effect sizes are not that great. The same is the case with mathematics. There's a tiny difference, but there's a huge variability across countries. And the interesting part is that these differences seems to correlate with the number of female researchers and female teachers and the degree of equality in those countries. So the more female researchers, the larger the equality in the society, the less of a difference you will find between girls and boys in their abilities within mathematics and science understanding. It actually turns out to be the reverse for reading. Here it goes in the opposite direction. Now, the more female teachers, researchers, the more equality, the larger the difference is in reading ability. So what this suggests is that there is a connection between society differences or cultural differences and also sex and gender differences. But it's not a neat pattern. It might level them out, or they might become increased. But what it does show is that these differences are affected by different cultures and probably different schooling systems, right? What about personality? Can we find any differences? Yeah, sort of. Again, they are not very large. And again, they seem to vary across culture. So they are probably not a product of biology, because if they were, we would expect them to be somewhat more stable than they are. So a couple of other things from meta-studies. The ability to inhibit behavior. Females tend to be somewhat better than men. But remember again, these are graded differences. They're not class differences. Men are a bit more impulsivity, higher level guys than women, and we're also more helpful to compensate. I don't know why. Women are a bit more anxious, but also more tender than males. And males are, again, on average, more aggressive than females. And here's the point. I promised you to get back to something regarding hormones. And how many of you think there is a connection between aggressiveness and male hormones? Testosterone, for example. Please raise your hand. Yeah? How many of you think that there is no such connection? Ooh, we have a winner. So I'm happy to be able to debunk that one. There is no connection. It is true that men on average are more aggressive than women. It is also true that men have higher levels of testosterone than women. But actually, the difference in aggressiveness, the sex difference in aggressiveness, cannot be tied to differences in hormone level. Actually, there's no connection. not even within the sexes, between the degree of, or the level of testosterone and aggressiveness. So it must be coupled another way. So let's get to the brain differences, finally. Is there a difference? Yeah. At least there's one difference. And it has to do with size. Men's brains are on average larger than females' brains. And this is also true for girls and boys, actually. Does it relate to cognitive differences? Well, you can figure that out for yourself. Given that there apparently are no real cognitive differences, the answer is probably no. And the answer is, therefore, no. There is no relation between brain size and cognitive ability. Some people claim that the male brain is just less efficient than the female brain, so we need a larger brain with more cells to be on par with women, right? But the truth is, it probably reflects body volume. The larger you are, the larger your brain is. It might be as simple as that. And then a couple of years ago, I would have told you about another difference between the sexes that concerns brain maturation, with boys lagging behind the girls in brain maturations. It turns out, no, that was actually not the case, because this difference does not pan out in neuro studies. And that's just how science is. Science is a picture of what we know here and now. What I'm telling you today might be somewhat different that I'll be able to tell you from in a year or two, perhaps, but probably not that much. But this is one of them. Does this really mean that there are no differences between male and female brains? No. There are many differences. The point is, they are not stable. We have no such thing as a male brain or female brain. We have brains that differ in terms of how feminine or how masculine they are in different areas. And I would like to see if I can drive this point home with a particular study conducted by Gerlach a couple of years ago. What they did was to scan a lot of people, 281 to be precise, and measure the gray matter volume in 116 different regions of the brain. So 169 females and 112 males. And what they did then was to examine, is there a difference between the two sexes in any of these 116 regions? And there was. There were several regions that turned out to differ between the two sexes. So what they did was to order these regions. If we really had a kind of male brain and a female brain, you will imagine, or you would expect there to be some consistency. So if you score high on the feminine spectrum in one area, you should also score high on the feminine spectrum in another area. But it turns out there is no such connection. So this is what this kind of busy graph shows you. So here you got each individual. Here you got all the women. Remember, more women than men. And here you got one region, the second region, the third region, and so forth, of the 10 regions that showed the largest difference. And if there was consistency, you would expect the same color going through, but you don't. So it's actually possible to score high on the feminine spectrum in one brain region and not so high on the feminine spectrum in another brain region. Or even worse, depending on how you look at it, you might score high on the feminine spectrum in one brain region and high on the male spectrum in another brain region. So we don't have two brains. We got a lot of different brains, just as our faces are different. It's not possible to tell just from looking at the brain whether it belongs to a male or to a female. So no consistent difference, but a lot of individual differences. So imagine if we did this study once more, but this time with the new group of people, what would we find? Probably we would find something quite similar in the sense that we could find areas that differs between the two sexes, but there will be inconsistencies, not just in terms of whether you score high on the same part of the spectrum for two regions, but it would be possible that it's a whole bunch of new regions that turned out to show a sex difference. Probably because the differences we see are primarily individual differences, and they are affected by culture, and culture is really what differs between many people, and that shapes their brains in different ways, but in no way that is systematically related to your biological, genetic, sexual makeup. Right. So, I'm actually at the conclusion. Even where reliable gender differences in cognition can be found, and there are few, as I have demonstrated, they constitute differences in degree rather than kind or class, if you will. And just because a person is within the feminine part of the spectrum in one dimension, that could be in terms of a cognitive ability or a brain region, that doesn't mean that the same person will also occupy the same part of the spectrum for another cognitive ability or another brain region. So, to put it bluntly, just because you have a beard doesn't mean that you're particularly good at finding your way around. In short, gender is a very poor category to use if you want to predict a person's psychological or cognitive abilities. It just doesn't work that way, because the differences we see are psychological differences, and they're primarily individual differences and not determined by which sex you have. So, why the beep do we do it? Why do we think in classes when they do not always fit? We do it because often they do fit. And we like to classify things. And why do we classify things all the time? We do it because we like to predict the world around us. If I can predict what's going to happen, I can feel comfortable. I can relax. But if I can't predict things, I get nervous and uncomfortable. And we use categories to classify things so we can know what to expect. And often it works. So imagine you meet this fellow. What do you think? Do you panic? No, you just say, well, that's a pig. I know that. It can run. You can use it for making bacon, right? You might even know it's a mammal. And if you know it's a mammal, you can also deduce that it has heart, blood, and hemoglobin. Well, you might never have thought of it. How many of you have thought that pigs actually have hemoglobin? Well, one. Good. But the rest of you could deduce it from the knowledge you have within your semantic memory. Because each concept presented in semantic memory is connected to related concepts. So you have a lot of knowledge lying latent that you can actually start to reproduce and use to predict the world. This is what stereotypes are also about. They are quite handy. Imagine now that you're walking down some road, could be in the city of Odense, not very likely though, and you meet this guy. Now you panic, right? What the f is that? But just for a short while, and then you say, okay, I've never seen that before, but it looks like a pig. And if it looks like a pig, it probably behaves like a pig. Okay, it can probably run, it's probably a mammal, it has heart, blood, and hemoglobin, even though you've never seen it before. That's pretty damn smart. The trouble comes now. You see this one, and you think, oh, I know that. It works like this. Or this one, seen that before. I know what to expect. And that's the trouble, right? Because you are now using a biological class to predict something that does not behave like a taxon. You're using it to predict something about psychology, and it doesn't work that way. So you need to refine your conceptions about how these things are connected with the taxon concerning biological differences. Don't use biology as a proxy for psychological differences. It simply doesn't work.